So I'm back. I was here last in November, and I ended the talk talking about the James Webb Space Telescope. How many of you were here in November that night? Okay, good. Not too many of you, because I'm going to repeat a little bit at the end some of the news from the beginning. But I know it's late. You've all been here for a while, so I wanted to wake you up with a song. If it'll work, we'll see.
1, 2, 3.
Well, it travels round the world from Greenbelt to California. It's getting on its sunshield before it launches up to space. She'll go on up to L2 and find some galaxies for you.
Tell me where in the world is
the James Webb Space Telescope. The mic drop was a little early on that one. Thank you. So we're going to talk about the James Webb Space Telescope. It has been on the move, not quite up into space yet, unfortunately, but it's getting close to there. So we'll get to that. So first, I'm going to talk to you just a little bit about science. I've had a lot of science today, so just a little bit of science about what I do. So what I do is not make pretty pictures like this. This is a visualization by John Wise from Georgia Tech University of what we think the distant universe probably looks like. So if we look in the distant universe, there are lots of galaxies. These are the bright spots around here in these clouds here. Here's one, here's one. There's lots of filaments of gas connecting these galaxies. And this is really, really early on. The universe was much smaller. It was much more dense, much more compact. It was just a happening place. A lot of great things were going on. Lots of stars were forming. Lots of galaxies were colliding. And I tried to look at that with a telescope. And then I go talk to my colleagues like John or other people like Professor Brahm here at UT and try and figure out what are our observations telling us about this early universe. So if we want to study that time, we're talking about more than 13 billion years into the past, talking close to the Big Bang, which is not as controversial as our friend in the blue hat may have us believe. We really need the best telescopes. Okay? And so right now, the best telescope, well, there are a few best telescopes, but my favorite is the Hubble Space Telescope. And that allows us to take images like this. Does anybody know what this is called? The Hubble Ultradeep Field. Yes, it's a question I ask in literally every talk I give. What is this image? This is the Hubble Ultradeep Field. This is what happens when you take our best telescope, which is right now a 2.4 meter diameter telescope. It's about yay tall from here to the floor. It's not actually all that big. You put it up into space so the silly atmosphere isn't in the way. You open its shutter and you stare for a few hundred hours. And you see that the universe is seemingly filled with galaxies. So pretty much every single thing you see in this image is a galaxy, except this one right there. There's a star. There's another one hiding somewhere. But all the rest of them are galaxies, and that's great. We can learn a lot about the universe. But I say, this is not enough. I want to see more. When I look at this image, I see, look at all this empty space between all these galaxies. Serious. It wasn't a joke. Look at all this empty space between these galaxies. Is it really that there's nothing there, or have we just not tried hard enough? Okay, so let's take like $10 billion of taxpayer money and try harder and see what we can find. All right, so we need a bigger telescope. So we're not just guessing. When we go back to the simulations, those beautiful movies I showed you, they tell us that there are lots of really tiny faint galaxies early on, and that galaxies start forming impossibly early. In fact, we heard about in the news this EDGES experiment. They predict that stars started forming just a few 100 million years after the Big Bang. The most distant galaxy that we can see in this image is maybe 500 or 600 million years after the Big Bang. And so there's a nice time space there that we're missing between, say, 2 and 500 million years. And that's not a giant chunk of the universe, but that does come from a time when the universe was extremely active. There's a lot of stuff going on, so we would like to look at it. So for that, we need a bigger telescope, and here is where Webb comes in. So this is our nice schematic, sorry I know it's a little low, showing us the size of Hubble compared to the size of the James Webb Space Telescope. So the primary mirror of JWST is big. It's 6.5 meters in diameter. You might say, wow, that's enormous, and it is for a space telescope. It will be the largest space telescope. It's not actually that big from the ground. The Hobby-Eberly telescope in West Texas that we know and love, that we own and operate, is 10 meters in diameter, so it's actually bigger, but it's in West Texas, which is beautiful, but you may know, or you may not, is not space. So it's not quite as good. It's nice, it's beautiful, it's a little windy, the conditions are good, but not great. So when we put things into space, it's a lot more expensive. So space-based telescopes tend to be smaller than ground-based telescopes. So right now we're building this great 6.5 meter space-based telescope, the University of Texas is also building a 25 meter ground-based telescope called the Giant Magellan Telescope. They will be very complementary. So what is Webb going to do? It's going to be big, which is great. It's also going to look in the infrared. The infrared are particles of light photons that are just redder than our eyes can see. So our eyes see visible light. Just redder than visible light is the wavelength regime that we call the infrared. And the reason why I care about this for distant universe galaxies is that because the universe is expanding, something we've already talked about today, everything is moving away from us. When something emitting light is moving away from you, the light waves actually get stretched out and appear redder to our eye. If something is moving towards you really quickly, the light waves get compressed and appear bluer. So here I have a red laser. If I was to shine this in your eye, which I won't do, but if I was to shine it in your eye and run at you at an appreciable fraction of the speed of light, which I also can't do, it would actually start to appear blue. Okay, now if I ran away from you, it would go from being red to actually infrared. And that's what galaxies are doing. Really distant galaxies are moving away from us so quickly that the light that we want to see from them is shifting into the infrared. When we look at a distant galaxy and we measure its redshift, its distance, we give it a number called a redshift number. That's the left column. I think this is the only numbers I'm going to show you today. That's the left column of this table. Okay. What this is really telling us, the right column is a little bit more intuitive. It's telling us how far back in time we're looking. And so if we look at a galaxy that is not redshifted at all, that means its light is not being stretched at all. We're seeing it at a time 13.8 billion years from the Big Bang, which happens to be when? Today. Hey, today. Very good. Okay, and that's a redshift 0. We live at redshift 0. Congratulations. If we go back to a redshift of 1, this is where all of the wavelengths of a galaxy's light are essentially getting doubled. All of the distances between successive wave peaks of light get doubled. Okay, then we're looking 6 billion years from the Big Bang. It's actually a long time ago, but it turns out the universe is pretty empty these days. Not a lot is happening. Hubble, it turns out, is sensitive to galaxies from about redshifts 2 to 8. Can do great work there. It's also sensitive to galaxies at lower redshifts. It's kind of complicated. We won't talk about that. But it's definitely not sensitive to galaxies at redshifts greater than 10. And that means Hubble cannot tell us about the first 500 million years after the Big Bang. For that, we need a telescope that's sensitive to redder wavelengths, and that's the James Webb Space Telescope. That is the number 1 reason, exoplanet people be damned, that is the number 1 reason why, the exoplanets will probably get the majority of the time. Can argue about that, ASAP Rocky Planet. But that is the reason why this telescope was built, was to find galaxies in the early universe, to find the first galaxies. So what is this telescope? This is not the telescope. This is a scale model of the telescope, but that's okay. It's big. Its primary mirror is 6.5 meters in diameter. It's a space telescope. Funny story, you are all glowing in the infrared right now. How many of you knew that? Okay, you've heard of night vision goggles, right? Night vision goggles are just infrared goggles. They just show us what is coming out in the infrared. Our bodies all glow at around 10 microns, which is somewhat redder than our eye can see. Okay, Webb would love to study galaxies at 10 microns. It's not going to be able to see them very well if it's hanging around the Earth that is also glowing, at about 10 microns. Okay, so Webb needs to go not just into space, but it can't hang out in orbit around the Earth because the Earth is really bright. So it's going to go to a place in space known as the second Lagrange point, or L2. It's a lyric in the song, okay, Grammy-nominated song, which is about 1 million miles away. So Webb is going to go 1 million miles away from the Earth, and the reason why it's going to do that is because it wants to put this thing on the bottom, the sun shield, also in the song, between it and not just the Earth, but also the sun, and also the moon. So Webb is always going to be pointed away from the Earth, the sun, and the moon. All those bright, annoying sources of light are going to be behind the sun shield, towards the ground. Okay, so let's talk a little bit about what Webb can do. So here's our beautiful Hubble Ultradeep field with all these depressing blank spots. Okay, we're going to now put our larger telescope into space, and we're going to expose for several hundred hours. I don't know how long it will take us to be able to do this. We're actually, some collaborators and I, there's a proposal deadline in 2.5 weeks. It's extremely stressful time right now. Surprised that I'm actually here doing this instead of writing a proposal, but that's okay. I agree to it. We're actually trying to propose to this observation right now. Probably won't happen in the first year. We're kind of shooting high, but it will happen in the first few years. What if we stare for just as long as Hubble did at a similar region of space? What should we see? This is a guess. Now all those depressingly empty regions start to fill in with tiny little specks and dots, which are all really small galaxies that are really far away from us. Okay, very, very beautiful. So this is a guess. This is what we think will happen. So let's talk about the telescope. Okay, and the first thing I'd like to tell you is about where was it built? And I'm going to throw some acronyms at you like Otis. So I've been on some NASA calls lately, and they like to throw around acronyms. They were talking about Otis. I had to look up what it is. It's not a dog. It stands for, it's actually a combination of two acronyms, the Optical Telescope Element, or OTE, and Integrated System Instrument Module, ISIM. Otis is a combination of those two. So the telescope, or the optical telescope element, the mirror thing you've seen, was constructed at NASA's Goddard Space Flight Center in Greenbelt, part of the song. Okay. The instruments, which are all placed into ISIM, were built at various places. So NIRCam, I'll show this in a second, University of Arizona, a bunch of places in Europe, NASA, and Canadian Space Agency. Okay. So dozens of astronomers, or probably more like hundreds of astronomers, poured years of their lives into building these instruments. And they got grants to build them, so they were paid. They didn't donate their time. But they did still spend their careers to build these instruments. And as I will tell you in a bit, they were rewarded handsomely, not just with grant money, but with something else. And we'll get to that. The spacecraft itself, that's the part on the bottom, which helps it steer. That was built at Northrop Grumman in Los Angeles, California. And the rocket, the Ariane 5 rocket that will launch it into space, was built by our friends the Europeans, actually specifically by the company Airbus, in a variety of places across Europe. This is sadly not an image of Webb being launched because it hasn't happened yet, but this is an image of an Ariane 5 rocket. How many of you know the story of the last launch of the Ariane 5 rocket? Did not go so well. So it was launching satellites into Earth orbit. They made it into Earth orbit, but they made it into the wrong orbit. Luckily, we are not the next launch. Well, sadly, but luckily, so they have some time to figure this out. So let's talk about what Webb has been doing. So Webb, as I mentioned, was built in Greenbelt. A while ago, it actually moved from Greenbelt to Texas. Here, Texas. It's no longer here, sadly, but that's a good thing because it's gone on its way. So Webb went from Greenbelt, Maryland to the Johnson Space Center, in Houston, Texas, for a very specific reason. When Hubble launched, it had a problem. What was the problem with Hubble? Its mirror didn't work right. So when Hubble was launched, they did not do the complete end-to-end optical test to fully understand the shape of the mirror because it was too expensive. And it turned out the mirror had a flaw. Luckily, Hubble was in Earth orbit, so they were able to install effectively a contact lens to fix that shape. Webb is going 1 million miles away. We can't fix it. Even if it was in Earth orbit, all our space shuttles are in museums, so we couldn't fix it then anyways. We certainly can't fix it 1 million miles away, so we're not going to skimp on that. About half of Webb's $8 billion budget is in testing, and part of that testing was to do this end-to-end optical test. The problem was this thing is gigantic. They had to find a room big enough not just to fit the telescope, but to fit the telescope in an environment that is similar to space. So they needed a vacuum chamber where they could suck all the air out and make it very, very cold. The movie will tell us, I think it got down to about 40 degrees Kelvin or something like that. And that was at Johnson Space Center. That was Chamber A where the Apollo astronauts trained. It was being unused. It actually had this historical plaque on it. It was all dusty. They spent the past few years cleaning out. They ripped the plaque off the wall. And just over the past 6 to 8 months, it was there. It was in Texas. And here it is actually sitting inside the chamber. That is the telescope. That is not a scale model. This is it. Okay, we can't drop it, and I'll show you pictures of it hanging in the air. It's kind of scary. Luckily, it's sitting there now. So now I'm going to show you some videos of the telescope at Johnson Space Center. So here it is. We'll see it come in. This is its shipping container. Okay, it went there on an airplane, a big airplane. Now it's out. Now it's hanging in the air. Actually, no, sorry, it's sitting on the ground. Then they're going to put it on this thing, and they're going to wheel it in. And this is all to test. Here's ISIM hanging off the back. Here's where the instruments are. Lots of people moving around. This whole process took several months. Actually, during Hurricane Harvey, it was in the vacuum chamber during Hurricane Harvey. Some of the astronomers I know who work on the instruments were sitting there sleeping overnight by the telescope, like armed with mops in case they had to keep water out of the vacuum chamber. Water going into the vacuum chamber, that's a problem with your vacuum chamber. Okay. So you see these struts here. These are holding the secondary mirror. Light from the really distant galaxies I want to see bounces off the primary mirror up to the secondary, back through the hole in the middle to the instruments back here. It's getting ready to go in. Takes a little bit of time. I'm going to take a drink of my beer. This video is a little anticlimactic because it's in there for something like a couple weeks, and it happened in about 5 seconds in the video. But that's okay. Now it's in, which is great. Getting all ready to close the door. They'll close the door. They'll cool it down to the temperatures of L2 soon, almost, probably now. Hey, look at that. There it goes. And now they're heating it up. Let's take it out. And it passed. Everything was fine. The mirror works. Of course it worked because we paid to test it. They also did some cool stuff like vibrational tests. They tested it against G-forces that were several times that it's expected to experience on launch, and nothing broke, which is good. And so it was ready to go. So put it up into space, right? Not quite yet, because right now all we have is a telescope. If we launch it up into space, it's just going to slowly spin and not do anything. We have to attach the spacecraft. Where's the spacecraft being built? You remember? Los Angeles. So we got to fly this thing to Los Angeles. So let's fold it up and put it on an airplane again. So here it is. The mirror is all folded up. This is what it's going to look like when it's packed into the rocket. It has to fold up to fit in the rocket. Here are these very, very careful engineers putting it back in its shipping container. Closing the shipping container. Has an acronym that I can't remember. Shipping container, I'm sure, was extremely expensive. Moving it very slowly. Sometime in the middle of the night in Houston, I was going to a military base right near Johnson, so I didn't have to block the road too long. Ironically, totally different talk, maybe I'll give it some time here. The giant Magellan telescope mirrors had to move through streets in Tucson. It was actually wider than this, and they had to close the streets for that. So here it goes onto a cargo plane, loaded up in there. Here it goes, no room for passengers. Make the relatively short flight to LAX, where it landed in, yeah, you see there's not a lot of clearance around that thing. Now it's in there. Buckle its seatbelt, send it on its way, and there it goes. Don't crash, please. Also, there are people on the airplane. Care about them too. And here it is 3 hours later at LAX, unloaded. I think we'll see it going through the streets at high speed yet again, just like the Rose Parade. And then it gets to Northrop Grumman. And we will see it there. And last time I gave this talk, a couple weeks ago, ironically in Houston where I gave this talk, that's where the telescope was. It was sitting in the clean room of Northrop Grumman, still in its shipping container. But 10 days ago, I received illicit, not yet public photos of the telescope coming out of its shipping container. And I was so excited to share them with you until NASA released these photos 4 days ago. So they are public, and you can go see them on their website. But I'm still going to show them to you in a second when this video is over. So here it is. Lots of words. All right. Honestly can't remember if there's anything else interesting to see in this video. Nope. All right. So here we go. All right. And picture. Here we go. They're taking it out. So this is a picture from just about 10 days ago of them taking the lid off of the thing. The mirrors are still there. They look like they're in place. That's good. Let's lift it out and dangle it precariously from the ceiling. Hey, look at that. And there it is. And now they're going to get ready. See this in the background? This is the actual sun shield. I didn't even notice it when somebody showed me this picture. Somebody who works at Northrop Grumman. This is the actual sun shield right there. It's all folded up. They're going to pair it together. They're going to pair the telescope, and they're going to get ready to launch it into space. So let's take a look at the roadmap of Webb. So here it actually is at Goddard, built at Goddard, went to Houston, got tested, passed its test with flying colors, onto Northrop Grumman, where it's getting paired with the spacecraft. Then it needs to go to French Guiana. French Guiana is on the northeastern coast of South America. I learned this. This is the only part of continental South America that is like not its own sovereign country. It's part of France, French Guiana, as you might guess. To go there, it is too big to fit in an airplane, so we got to stick it on a boat. You might notice it's on the west coast of the US, has to get to the east coast of Africa. It is not going to sail all the way around. It's going to go through the Panama Canal. Sorry, what did I say? Oh, no, it's not going to South Africa. South America, thank you. See, you're paying attention. That's good. All right. Where it's going to go to Kourou, which is the launch facility that ESA, or the European Space Agency, owns. They wanted to get in on this telescope, so they said, hey, we'll give you this $400 million rocket. Can we please use your telescope? We promise we won't ruin it. That's what they say. And this is, again, what we hope will happen. Probably. So this says June 2019. It's going to take a little while to pair it with the spacecraft. Specifically, they've had to do some work on the spacecraft. There were some leaking fuel nozzles. That's bad. So they fixed that. The sun shield snagged a little bit. Also bad. They're working on that. Probably it will happen a few months later, maybe early 2020. That's all okay, because you want this to work, okay? The entire foundation of United States astronomy is based on this telescope working. It's got to work. If it happens 6 months later, totally fine. Okay, so nothing will go wrong. It will launch, all right? So I'm going to show you some dates now, plus or minus, well, probably not minus, plus 6 months maybe. That's fine. All right, so if it launches in, what did I say, June of 2019, they need to, well, actually, first they need to fly the telescope to L2, which will take 3 weeks, unfold the thing, which is crazy and scary. And then they got to test it. They got to calibrate it. They got to figure out how it all works, make sure the mirror is unfolded, make sure the instruments are all working. They've allocated 6 months for this process called commissioning. After that, we will start observations around December of 2019, plus 6 months, maybe, maybe not. And let's come back to those scientists. So scientists who dedicated years of their life, decades of their life to building these instruments, and they were rewarded with something called guaranteed time observations. That meant that these groups who built these instruments get to observe whatever they want to, and they have differing amounts of time to do this. And not only do they get to pick what they observe, nobody else gets to see these data for 1 year. This data is proprietary. Okay, and the sad truth about the Webb telescope is the baseline mission is 5 years. That means if it lasts 5 years, NASA calls it a success. It almost certainly will not last more than 10 years. And the limiting part of the lifetime for Webb is the maneuvering fuel. It needs to be able to station keep out of L2, and once it runs out of maneuvering fuel, it's going to have trouble pointing very well. Okay, so we've got 5 to 10 years with this telescope. A lot of data is going to be taken in the first year that we won't see. Okay, and that's okay. They've earned it, right? We didn't have these people. We wouldn't have these fantastic instruments. So that's okay. But as I'll show you, it's a lot of time. So the team that built the spectrograph, NearSpec, 842 hours. I should tell you, in 1 year, there are about 5,000 hours of time they can give away. 842 hours to the NearSpec team, 1,030 hours to the NearCam team. Here they are observing one of our favorite fields. We call this licking the donut. They're kind of observing it all over, so we can't get in there. And that's okay. The MIRI team, the mid-infrared imager, that's the one that wants to observe at your body temperature at 10 microns, 600 hours. And interdisciplinary scientists, these are people that have been helping with the mission. They didn't build an instrument, but they've been helping to find the mission for decades, 400 hours. And they're going to do interesting things like look at Titan, which is kind of cool. All right. So if you add all this together, this is about half of the first year's observations. Okay. Nobody gets to see it other than the people on these teams. Okay, and they have priority. If you want to look at Titan, you can't do it. They're already looking there. Okay, and you can't see it for a year. So, right. So this is a problem for the rest of us, the have-nots. I should be fully honest. I'm actually on one of these interdisciplinary scientist teams, so I have access to 100 hours of data, which is great. Thank you, Roger. All right, it's great. But still, there's a lot of data we can't see. And so because of this, this was realized a few years ago. The director of the Space Telescope Science Institute, who that institute, it's in Baltimore on the campus of Johns Hopkins University. They run Hubble. They're going to run Webb. He created a program called the Director's Discretionary Early Release Science Program. So the director of the institute, it's a pretty sweet gig. You get 500 hours every year of this telescope to do whatever you want with. And they always do very cool stuff. Programs like the Hubble Ultradeep Field. In cycle 1 of James Webb, Ken Sembach, who's the director now, decided to do this early release science program. And he decided that he wanted to allocate up to his 500 hours over 12 to 15 programs covering all areas of astrophysics. And the goal was to get data in the hands of the entire astronomy community ASAP. So that means these data all become public immediately. The second they're downloaded from the telescope, anybody in the world can download these data. So very different from those guaranteed time programs. The proposals were judged heavily by how well they tested multiple modes of the telescope and also their plan for rapid data releases. So if you submitted a proposal for one of these programs and you won that proposal, you don't just get to go do your science in a corner. You are responsible for releasing reduced high quality data products to the community very, very quickly within just a few months after you get your data. In addition to a great management plan, you also had to be the most interesting scientifically. Okay, so this is a little bit different from a normal proposal call where you just want to do the best science. Here, doing the best science was just like getting your foot in the door. Then you had to say, here's how we're like awesome managers, and we're going to do really awesome data releases and have a cool website and all that kind of stuff. And so this proposal was due last August, and so I was, of course, interested. So I worked with a group of 100 of my closest friends to craft a proposal that we called the Cosmic Evolution Early Release Science Survey, or SEERS, because we are seeing into the early universe. Astronomers love our acronyms. And on the morning of November 13th, I got this awesome email. I didn't need to read past the third word here. Some of you have known it either says, please, we are pleased, or we regret. After that, you don't need to read. And so, yes, we were lucky enough to get this proposal approved. So we have 63 hours of observation time with Webb. Whenever it launches, this data will be obtained in the first 3 months. Is that a question? Don't forget the point 2. It's actually 63.7. I lobbied hard for an extra 30 minutes. Long story. But as you can imagine, this was extremely difficult. There was a lot of interest in this. There were about 106 proposals There were 106 proposals submitted, 13 were accepted. And so I'll tell you a little bit about SEERS, including our awesome logo that was designed by the College of Natural Sciences at UT Austin. As I said, we have 105 people from around the world, including 10 countries and 28 institutions just here in the US. And I'm just going to show you a couple illustrative figures of what we're going to do. And so imagine you wanted to look at a galaxy at this extremely special wavelength of 3.6 microns. Okay, this is redder than our eye can see, but not quite as red as your body emits. It's a cool wavelength. You just have to trust me. You can see kind of like cooler, older stars at that wavelength. And you looked with our best telescope now, which can observe there, which is not Hubble. Hubble can't get anywhere near that red. That's the Spitzer Space Telescope, size of a trash can, been flying in space since 2003, I think, 2003. This is what you would see. Beautiful, right? Some pixels. This is what you would see with the James Webb Space Telescope with the near-infrared camera and NearCam. Okay, so hey, there's a spiral galaxy hiding in there. Say you wanted to go even farther into the infrared and look at 24 microns. Again, the best we can do right now is with Spitzer. At bluer wavelengths, sort of closer to what your eye can see, there's a whole lot of galaxies there, but you don't know what they look like here. These are stars. At these wavelengths, you're actually seeing hot dust emit. And that tells you a lot of cool stuff about star formation. But again, with Webb, we resolve out all this cool stuff. So we're going to see a lot. And as I said, this is just one of 13 programs. In fact, UT was represented in 5 of the 13 programs. In addition to my own, there's one looking at nearby galaxies. There's one studying 4 very cool galaxies in extreme detail, and then some very cool exoplanet stuff, one taking direct imaging of exoplanets. All right, I know I'm on video, but don't quote me on this. All right, one taking very cool imaging of exoplanets, and one doing something called transit spectroscopy, where we try and actually study the atmospheres of exoplanets. So all of these will happen in the first 3 months of observations after Webb, in which I'm sure we can all come back. We'll have a different talk for each of these at Astronomy on Tap in 2019 or 2020, whichever one it is, and we'll be glad to come talk to you about that. So that's all I have, and probably have a little bit of time for questions. Yeah.
Steve. All right.
Steve.
We have time for 2 questions. 2 questions right there. Eager hand.
Is there any optical or visual benefit to having the mirrors or lenses in a hexagonal shape, or is that all just for packaging and assembly?
Yeah, so the question was, is there a benefit to having the mirrors and the hexagons? You would rather have one single dish. That single dish will not fit in the rocket, so it has to fold up, and it turns out if you're going to fold something up and butt them together, hexagons make great shapes for doing that. If you were to butt circles together, you would have all these little gaps in there, which is what we're actually doing with the Giant Magellan Telescope. It's not the end of the world, but this is just one way.
Okay, right there.
Yeah, so the question was, they said they're not going to be able to refuel the rocket. Is there any possibility of that? I ask this question all the time because this telescope is so expensive. Certainly, you would think, with all the cool things that I'm sure our maybe military does in space, we should be able to go, we can refuel satellites in Earth orbit right now with robots, right? We ought to be able to do the same thing a million miles away. There is no money in the budget for this. And Webb got cost capped by Congress earlier this decade when it also got canceled. So Congress tried to cancel it, decided not to cancel it, but they cost capped it. So technically there is no money in the budget.
Thanks, Obama.
That is all I know.
Okay, if any more questions? Oh, one more question. We'll do one more.
How are you going to prioritize the 63.5 hours that you get?
I want to find the most distant possible galaxies that we can do, that we can find. That is how we're prioritizing it. Really, really deep images.
Yay, galaxies. Woo! All right, let's thank Steve one more time.
Steve.
Steve.